So, thank you for the introduction. And first of all, I would like to thank the organizers for giving me the opportunity to speak about some results which I achieved very recently, although they have really nothing to do with the topic of the conference. But if I look at the audience, I see many experts in finite elements, and maybe there is some interest also in this talk. In particular, I would like, and I'm happy to mention my co-authors. This is Patrick Ciarlet from ENSTA in Paris and Charles Dunkel from Virginia Tech. I started this project quite some years ago with Patrick, and then it turned out there are so much algebra involved that it would be good to have an expert in algebra, and then Charles Dunkel joined us, and we derived here some results. So the question is very old. I think everyone has come across a paper of Crouzeix and Raviart in 1973, where they introduced their non-conforming finite elements. This is now 44 years ago, and surprisingly, at least I have not found basis functions or representations of basis functions for general order P, general polynomial order P, and I got interested in this problem, and it turned out that there is one step in the construction which is somehow beyond analysis, or another field, namely in algebra. One needs some pieces of representation theory in order to construct them, and maybe this was a reason why this natural question to construct this basis for Crouzeix and Raviart has not been treated. But of course, one is never sure. Maybe someone of you raises a hand and tells me he or someone else has done that 20 years before. I'm prepared for that. Okay, so I will speak about non-conforming HP finite elements, and this somehow involves a lot of notation, because I speak about 3D problems, and therefore I warn you, the first 3 slides are a bit boring because I introduce the notation, but I hope that afterwards it will become better. So in order to introduce these non-conforming finite elements, I'm using the most simple model problem which is appropriate to explain them, namely the Poisson model problem with a diffusion tensor A, where we assume proper bounds from below and above. So this is our model problem, and I focus mainly on the 3-dimensional case. So as I promised, boring notation. G is my mesh, H is my HK is my local mesh size, H is my maximal mesh size, and in 3D I consider simplicial meshes. That means you have facets which are called T because the facets are triangles and collected in the set F like facets. Then you have edges, and then you have vertices. Okay, so, and you have indices here, whether these objects are lying in the interior of the domain or in the exterior of the domain. I will repeat this notation during the talk if it becomes necessary. And then it's very simple to define the conforming HP finite element space. I had 0 boundary conditions, which are somehow this restriction 0 at the boundary is with this restriction, continuous functions and polynomials of degree p on each element. So very standard. And if one wants to compute, one needs a basis. This is somehow an implicit definition, and one needs a basis, and of course we all know this concept of affine equivalence. One goes to the reference element. Quantities on the reference elements always have a head on top, and these affine pullback. So I can be brief because I only introduce here notation, and my basis functions of course depend on the mesh, depend on the polynomial degree, and I consider here Lagrangian finite elements. That means n is the nodal point where the function is located, so one has a characterization via this condition. And then this basis allows to split the conforming finite element space into local bases, which is the main point for the computational efficiency of finite elements, that one has a local basis. These are the basis functions which are supported on a tetrahedron. These are the basis functions which are supported on two adjacent tetrahedron, that means facet or triangle oriented. Then there are basis functions which are supported at all the tetrahedrons which shares a common edge. And finally, these basis functions have the largest support. With the vertices, you have all the tetrahedrons which are attached to this vertex. Okay, that was it with the notation. This is an important property, that this implicitly defined conforming space can be written as a direct sum of these local spaces. Okay. Now I switch to non-conforming finite elements, and there is this seminal paper of Crouzeix and Raviart from 1973, where they introduced non-conforming finite elements in an implicit way. And I have to admit, I learned non-conforming finite elements from the father of Barbara Verführt. And he did these non-conforming finite elements, and he did this analysis, of course, in 2D, which we all know, and the lowest order Crouzeix-Raviart element, where you say the functions are linear on each triangle, and you require continuity in the midpoint of the edges. This is, of course, in 2D. And therefore, I thought, okay, this is an element which Crouzeix and Raviart have introduced, but they did it much more general. They defined it. It is not important that you cannot read that, because it will be on the next slide in detail. They defined this space in an implicit way. Instead of this continuity requirement of conforming finite elements, which is easy to formulate for all polynomials of degree p, they weaken that and require some kind of moment condition. This is a hypothesis H2. And then they performed a general error analysis, which is now, if one looks in the book of if one looks in the book of Ciale, you find it under the name the second string lemma. You don't find it under this name in Sue's book. And I just talked to her, and I got this historic information. The second string lemma for the error analysis of non-conforming finite elements is due to Berger, Scott, and Strang, and was written in 1972. So 1 year before this analysis came out, and it's due to these three authors. Okay, but Ciale called it second string lemma. Okay, so what is it about? So this is for general polynomials of degree p, and they did it because this is an important application of their elements for the Stokes equation. And you find examples here of these spaces, namely this one, but also this one in general dimension, but still for polynomials of degree 1. And you find one example of polynomials of degree 2 for the two-dimensional case. Okay, so what is it about? So instead of the continuity of the functions across the boundary of the simplices, a weak compatibility condition is imposed. So first we have to introduce the notion of L2 orthogonal polynomials on triangles. So these are polynomials of degree p, which are orthogonal on all the polynomials of degree p minus 1. Here on the reference triangle, so this is a notation for them, and here it is explained. The L2 scalar product on the triangle should be 0 for all the polynomials which are 1 degree less. And the weak compatibility condition, which replaces a continuity condition, which is in the paper of Crouzeix-Raviart, the hypothesis 2, is that the jumps across the inter-element boundaries is an orthogonal polynomial of degree p, orthogonal to all polynomials of degree p minus 1. And if one is at a boundary facet, not the jump, but the trace itself should be an orthogonal polynomial. In 2D, what does it mean? This condition applies also in 2D. Then T is not a triangular facet, but an edge between two triangles. Say this one. That means the jump between two linear polynomials in this case is continuous here. That means the function looks like that. If I take this edge out in the one-dimensional case, the jump looks like that. And this is, of course, an orthogonal polynomial of degree 1, which is orthogonal on the constants. So this is in this slide. In 1D, you can do it also for higher degrees quite easily, because the dimension of the orthogonal polynomials in one variable is 1. Yeah? You have the Legendre polynomials. Legendre polynomial of degree p is orthogonal to all Legendre polynomials of lower degree, to all polynomials of lower degree, and the dimension of the space is 1. In 2 dimensions, the dimension is higher. The dimension is p plus 1. So on triangles, the dimension of the polynomials of degree p scales quadratically in p, but the subset of orthogonal polynomials, the dimension is p plus 1. So you have more, which makes the thing more interesting. Okay, so, and this is a definition of Crouzeix-Raviart. Very simple, but very implicit. So all polynomials locally of degree p which satisfy this weak compatibility condition. And the discretization, this is very nice with this non-conforming method. Practically one can stay with the old bilinear form without additional terms. Of course, one has to apply the gradient element-wise, because they are discontinuous across the facets. So very simple, very classical. Also the error analysis, a theorem in a similar form, is also in the paper of Crouzeix-Raviart and is based what is by most people called second string lemma, to estimate the residual which measures this nonconformity. And the important thing is, this is the HP finite element space which is conforming. This is the space of Crouzeix-Raviart with this implicit condition. And if you take any space in between, so S could be this one and this one, but any space in between, you get this estimate. This will be important later. Okay, this is so a repetition. I hope some time is left for new stuff. Maybe one remark in the proof where this orthogonality condition comes into play. And this is also what we teach in finite element courses. One does partial integration, and here we have the jump of the test functions. And this is exactly the point, I call this Wi. This is exactly the point where one can insert some polynomial on the facet of degree p minus 1, because this one is orthogonal on all these polynomials. And then by standard trace and Poincaré estimates, one gets this error estimate. But this is exactly the point where the condition, these functions should be orthogonal of all polynomials of 1 degree less comes into play. Okay, now implicit condition, but the question is, we want to have a local basis. And the first, what I thought is, and which is true, is a most simple case. We are looking for non-conforming basis functions of degree p, which are supported on 1 tetrahedron. So this is the subset of this implicitly defined space where the support is contained, or is 1 tetrahedron. And now this proposition should somehow be the motivation for the next part. It turns out that all the functions in this space, so the restriction of this non-conforming space to 1 triangle, if you look at the facets of the function, must be a symmetric orthogonal polynomial. I will explain that precisely what this is, because this should motivate to discuss this question, and this is a part where these algebraic questions come into play, because if you want to somehow have a parametrization in one big set of some kind of symmetric objects, this is typically not so simple. The same thing if you want to parameterize symmetric positive definite matrices is also not so simple. Okay, so before I frighten you with the formulas, I would like to ask to look at the formula with the classes, whether they are complicated to be implemented or whether they only look complicated. So, Jacobi polynomials are one-dimensional polynomials. They are well known, and they can be written down in a quite different way. And during the course of this research here, I found these hypergeometric confluent functions with this very nice notation quite convenient. But again, they look much more complicated than they are. They are polynomials of degree n, so set to the k, and here you have some kind of coefficients which are factorials. More precisely, this is a Pochhammer symbol, which is also a factorial. So these are the Jacobi polynomials, which are in 1D, which are orthogonal to these weights. This is well known since a long time. Now, the definition, or the first definition of orthogonal L2 orthogonal polynomials was done in 1957 by priori, and you have this formula. You need these Jacobi polynomials and evaluate them at some argument, here a rational argument, and here somehow affine arguments. So, and then one can prove, which is not so simple, it's worthwhile to look here in this paper because the proof is quite interesting. They show that these are solutions of some eigenvalue problem. I guess one can do that also in elementary fashion. These are these polynomials. And one property which will be important is this one. So at the moment I'm doing things only on the reference element. So I have this element, and these polynomials, there are two types. For even k, they are symmetric with respect to reflection at this angular bisector through the origin, and the odd ones are antisymmetric, right? So this definition uses somehow 0 at a special point. Yeah, you can make the definition simply with this and with this and with this, and but it's important to mention that this definition is somehow not completely symmetric in the triangle. You get the basis depends on the choice of the origin or of this point 0. Okay, so now let's proceed. And now if you consider these orthogonal polynomials on one triangle, they of degree p, I mentioned already, they have dimension p plus 1. And one can prove that the restriction to one edge defines a basis of all univariate polynomials of degree p. So in this sense, the set of orthogonal polynomials of degree p is isomorphic to the orthogonal polynomials of degree p in one variable. Or to put it in another way, if you specify here a polynomial, a general univariate polynomial of degree p, there is a unique continuation to an orthogonal polynomials. This will be important because in order to define these polynomials, Crouzeix-Raviart elements on one tetrahedron, one will glue these functions to the different facets. And it is then important to get continuity across the edges, and then this property will be used. Okay, now I come to the notion of totally symmetric orthogonal polynomials. Maybe don't look at the definitions. These are these polynomials which are invariant under affine transforms of the triangle onto itself. So if you take some kind of transformation, they should be the same. And interestingly, in the literature, these polynomials are not so well studied. Before I come to the construction of the basis of this space, so these are the symmetric guys in the space of all the orthogonal polynomials. I will try to explain why these are important. If we want to define Crouzeix-Raviart elements on this tetrahedron, what we will do is we take one basis function of a symmetric polynomial on this triangle. So this is the same under these affine maps. Then we map this onto this function, always the same, to the four facet, and then automatically, because they are identical on all the edges, you get a a polynomial on the surface of the tetrahedron which is continuous across the edges. So therefore, and then we will continue them in the interior, and then we have our basis for the simplex supported functions. So these functions will play exactly this role. Okay, and now we have the set of orthogonal polynomials. I have defined what are the symmetric ones. They will be important, but it is important to decompose this space into a direct sum, so that these two functions, these two spaces, they span the space of all symmetric ones. So the fully symmetric ones are, of course, a part of the mirror symmetric ones with respect to this angular bisector. But then we need additional basis functions which are only reflection symmetric. So this is already defined, and this one should span, should be the same as a span of those who are mirror symmetric. Okay. Now one has to understand how to define a basic for symmetric polynomials on a triangle. And well, the trick is as follows. You take a symmetric triangle in 3D with these three vertices, because then it's simple to write down the elementary symmetric polynomials. These are polynomials which are symmetric on this triangle, and every symmetric polynomial is spanned by powers and products of these functions. Okay, this is a general triangle in 3D, and it's very nice that, it's somehow quite intuitive that these symmetric functions look like that. And now one has to map that on this reference triangle. And with this mapping, one can check that. And then one sees E1 mapped to this triangle is the zero function. So only the power of 0 gives an interesting function, namely a factor 1. And therefore, only the back-transformed functions of type E2 and E3 appears. And you, as I said, you can raise that to powers A and B. And then you already see that the dimension of this space is not so simple. So I'm not speaking about orthogonal polynomials. I'm speaking about symmetric polynomials. So these have degree 2. So the total degree of this one is 2a. These have degree 3, so 3b. And if you want in total polynomials of maximal degree n, they are all combination of a and b, which is smaller than or equal to n. So it's clear that this is not such a smooth formula. Anyway, one can compute that, but for our purpose, this is not sufficient because we want to have the symmetric orthogonal polynomials. And well, then one has to do a little bit of module and representation theory. So the symmetric group is the group which contains 6 elements, all permutations of 3 different objects. So, and for a triangle, this is somehow isomorphic of all different permutations of edges. And if you can express that in our world of affine equivalence, you need 6 affine mappings to make all the possible permutations for a function. So one function is very simple. It is the reflection, which maps the triangle onto itself, R, so simply interchanging the argument. And these functions, which are symmetric because in that, are invariant under R, and M, probably you don't see it so quickly, switches somehow these two coordinates. So it's a reflection with respect to this angular bisector. And with these two somehow generators, you can produce all these affine mappings, and you can characterize this symmetric group also by writing down relations which these mappings satisfy. So first of all, since it's a reflection, twice application gives the identity, and one can also compute that MR to the 3 is the identity. And somehow it is hopefully clear that now the symmetric polynomials, for example, the symmetric orthogonal polynomials, can be characterized as eigenvalue problems for combinations of these operators, because they should be invariant. Okay, this is, I don't go into these details, but I simply present the result. So this reflection, one needs a basis representation, and the reflection is quite simple. If the index is even, it's simply changing the sign. So this matrix is a diagonal matrix with plus minus 1 on the diagonal. And this is for me still a miracle, but one can compute the basis representation, one can write the basis representation of the reflection with respect to this angular bisector in terms of this matrix, where again this coefficient here is involved. Okay, and then I want to be short here, not to run out of time at the end. It is important to understand these type of eigenvalue problems, RMQ equals Q, because these are then exactly the functions which are invariant under these rotations and reflections. Okay, so then it is an interesting fact that these eigenspaces are complicated to compute. One can prove that this is the image of this operator, which is quite simple. And this defines the matrix S, and then it is simply a basis transform. And the interesting thing is, if you have here even indices, you sum over the somehow even rows and columns of the matrix, and here's the other way around. Then you have defined polynomials here of degree k, and these are the basis of the symmetric orthogonal polynomials. So you have an explicit representation of these polynomials with some kind of coefficients. These are the standard basis functions, and this is somehow a change of basis. And then one has to understand how many of them arise, and then one ends up with these basis functions. And as I said, if one is one has such symmetric objects, then the dimension is complicated. The dimension of the symmetric orthogonal polynomials is this number, which is, as you can see, approximately n over 6 expressed a little bit in a complicated way. And maybe I can show you a funny thing, how this number came up, because I'm not an algebraist, but I was very much impressed. If you consider this function, at some point in this analysis, one considers this function and makes a Taylor expansion of this function. And then these coefficients are exactly the coefficients in the Taylor expansion. This I find quite beautiful, because otherwise, if you look at this number, it's not so simple to guess this formula. Okay, they look like that. These are the functions on the these are the functions on these orthogonal symmetric polynomials. And here I want to be short. I come directly to the picture. How is now the Crouzeix-Raviart basis function constructed on one simplex? So one has a formula which one should store in a program for a basis for the symmetric polynomials which are orthogonal of degree p. Okay. So then the corresponding, if you take such a basis here, then the element here on this tetrahedron is somehow you lift this function in affine way to these facets. So then you have polynomials on all the facets, and then you use this Lagrange property that a polynomial of degree p on a tetrahedron is defined by specifying the values in all nodal points. You have already specified the values at the nodal points on the surface. Therefore, you only have to specify them in the interior, and there you can take whatever you like. And at the moment, we have suggested to take 0 in the interior, only in the nodal points. But maybe for conditioning reasons, it could be more or better choices. And the functions look like that. I hope you see this is a tetrahedron, and these are these orthogonal polynomials which are glued together here. So I started earlier. How much time do I have? 4? Okay, thanks. Okay, now this was already very exciting, but of course this somehow analysis or theory should at least give something which is analogous to this 0th order Crouzeix-Raviart element. And I think also everyone knows the basis for the Crouzeix-Raviart element, how to draw it. If I have here two triangles, maybe I make a coordinate system. Then the basis looks like that. It is 1 on the edge here, or has a certain value, is 0 here at these midpoints, and it looks like that. Yeah. You know that. I cannot draw that. Yeah, it is continuous across this edge, and somehow it's an edge-oriented function. That means not a triangle-oriented function. So what does it mean in 3D? Now we take a facet, a triangle, which is attached, or a facet of two adjacent tetrahedrons, and we are asking to find the basis of the Crouzeix-Raviart elements which are supported on two adjacent triangles. And for this, we need a basis which are not fully symmetric, but mirror symmetric with respect to this angular bisector. Maybe I can be a little bit quick here because I don't want to go into this detail. This is the basis of the orthogonal polynomials, and one applies this operator, 2 times identity. R means interchanging the arguments. M means this affine transform. So these are simple somehow. This is an affine mapping, and therefore this means evaluating this at the affine transformed arguments. And it turns out one needs the eigenvalues of this operator, and it turns out that if you plug in this to this, you see that these are the eigenfunctions. This is quite simple if you use the relation, for example, that m squared is the identity, r squared is the identity, you see it immediately. Okay, so then you get some polynomials which are linearly independent. But the space, unfortunately, is, what means unfortunately, is bigger, and you have in total double the number. But this will not be important, only these functions will play a role. Don't forget about them. These functions play a role, and it's of course also important how many do you have. Yeah, at some point you get linear dependence. So how many are linearly independent, and then you find out this is this number, which is also some Floor n-1/3. And they look like that. So they are mirror symmetric with respect to this angular bisector, yeah, but not fully symmetric. Okay, and now now it becomes complicated, but I have here the drawing, but I cannot color it dynamically. So we have one triangle and two tetrahedrons which are attached. Then we have three facets on this side and three facets from the other side. And now let's look first at the three facets on this side. What one does is one takes a reflection symmetric polynomials, there one has an explicit formula, and one maps it in such a way that the origin is mapped to A. So they are then mirror symmetric with respect to this angular bisector, and if you do that with the same function on all three facets, you get a continuous function. So you have defined a function which is symmetric on these edges, and then you do the same from the other side for the three other facets. And then you glue them together and you get a continuous function on the surface. So, and this is exactly the analog then with this element. Here you have a function, you do the same from both sides. You have orthogonal polynomials and you glue that together from both sides. To be more precise, I cannot draw it. We are speaking here first how to define the values at the boundary, right? That means we know the function must be an orthogonal polynomial on this edge. That means a linear function which is 0 at the origin. Here as well, it must be continuous. I have to do the same here and here. And now I have to continue or to extend or glue them together from the other side so that we get continuous values here. And this is exactly this idea to put this 3 to the right side with the origin mapped to A1, and then to the other side with the origin mapped to A2. Okay, so this is by affine transformation. Then you have characterized the polynomials on the whole surface of this element, and then one can of course use again this principle of unisolvence of these nodal points, standard nodal points. Polynomial piecewise is uniquely defined by its values at the nodal points. I have assigned those on the boundary, and the inner nodal points you can choose whatever you like. And the simplest choice would be 0, but maybe for certain reasons this is not the optimal choice. Okay, so I think this was better to explain that with these pictures instead of formulas. This was this mapping. This is what I just defined. This is this principle of unisolvence. If you have it on the boundary, you get it also in the interior. And again, if you implement it, you write the reflection symmetric basis functions on the triangle. And then in order to define the function, the basis function on a pair of adjacent tetrahedrons, you use these affine maps, get the values on the boundary, and then you continue to the interior. And this is, of course, a whole support. This is a whole function. It is discontinuous then to the other simplices. This is clear. And that's some pictures how they look like, the tetrahedrons. The tetrahedrons are on top of each other. So you see they are symmetric with respect to these angular bisectors and glued together here in a continuous way. Okay, now interesting question was if we now throw all these non-conforming functions to the conforming functions, do we get linear independence? And the answer is no. The answer is no, and this can already be seen by this Crouzeix-Raviart element. If you take your conforming linear finite elements and you put in or inject the Crouzeix-Raviart element, they would be linear dependent. That means you have to remove all conforming functions which has a degree of freedom at the vertex. That means all the conforming functions for the P1 elements. That means with these discontinuous functions, you can linearly combine them in order to get the standard head functions. This is the message, which you can do. And here's the same thing. If you put in all the functions into the space, then you get linear dependence. So to be more precise, this is the conforming space. You can inject all fully symmetric functions, which are supported only in one tetrahedron. And the fully symmetric and the reflection symmetric are also linear independent, but exactly like here with this reflection symmetric, you can construct some conforming functions, and therefore this sum is not symmetric. So to cut the story a little bit short, we take only per phase set one non-conforming reflection symmetric function, only one, and leave away all the vertices, vertex-oriented conforming functions. And then we can prove that this sum is correct. So here I have removed the vertex-oriented conforming functions, and then one has here a direct sum. Okay, I will end up with also a question which I found fascinating. Now we have only looked at non-conforming functions which have support on one tetrahedron or on two tetrahedrons. Now one can ask the question, do these functions, together with the conforming one, span the whole Crouzeix-Raviart space? It's not clear. Maybe there are functions which are not so local. And the answer is, in very special topological situations, it can happen. Namely, in such a situation, which is special in the sense that every outer vertex has an even number of outgoing edges. Then you can have Crouzeix-Raviart functions which you cannot localize. But as soon as one vertex has an odd number of outgoing vertices on the surface, then this space span the whole space. I will end with a remark which is a reference to the theorem which I had, that the fact that we are in these certain situations not spanning the whole Crouzeix-Raviart space is quite harmless, because the error estimate was true for all spaces in between. Okay, so I was very excited to learn here so much about algebra, which was useful for this construction of these basis functions. And with this, I would like to end and thank you for your attention.